Okay, now I'm sure we're recording. So hopefully things will go more smoothly than they did the other day. And if not the first time in trouble, I'm going to reboot this dang thing. So for the next few class periods, we're going to get more theoretical about time-stepping methods for ODEs that we've seen, both one-step, and multi-step methods, um, and getting an understanding of when they converge and their order of accuracy, etc. Um, so we're going to break this down into um, this section 12.4 into three parts, three lectures for today, and then next Monday and next Wednesday. So today you're going to focus on consistency, and then the Monday stability and convergence, and then on the following Wednesday stiff differential equations. Now we've seen a little bit of convergence analysis, just a little bit. Uh, for the simplest time-stepping method of all, um, for Euler's method, um, proving that as the time step goes to 0, the error, which I'll define as En, equals, I'll do a notation check here. Dang it. There's actually different ways of defining error, believe it or not. Sometimes it's approximate minus the exact, and other times it's exact minus the approximate. Okay. So I use approximation minus the exact. That's a yn minus y of tn. So that error across all time steps. Alright, so n up to t minus t naught over h. So remember, t naught's the initial time, capital T is the final time. So this quantity is the maximum number of possible time steps, assuming we keep the time step fixed at h. So the error across all time steps, as h goes to 0, goes to 0. Okay. All right. Now, even though Euler's method is a very simple method, you may recall that convergence analysis, improving at this error goes to 0, as h goes to 0, is still quite tedious. It'd be nice to have a simpler approach to establishing that a method converges. So we're going to take a closer look at how to do this in a systematic way across all these different time-stepping methods, and it helps to break it down into three parts. Like with Euler's method, we just went to show convergence directly, but if we break it down into showing that a method is consistent and it is stable, then these two can be used to imply convergence, and I'll be able to explain how we show that a one-step or multi-step method is consistent, how to show it's stable, and then from there convergence will follow. So what do these things mean? So convergence is the only concept so far we've seen. Convergence just means that this error across all time steps goes to 0 as h goes to 0. But the related concepts of consistency and stability are quite important and very helpful in establishing convergence. So to help show that either one-step or a multi-step method, and we'll consider both of these but separately, is convergent. Okay. We use these related concepts of, I'll start a bulleted list here. All right. First concept I'll introduce is local truncation error. Now, these three concepts I'm going to show here, there is a definition of all three here in the text. But what I'm going to focus on here in the notes is, this is rather tedious to follow, just a informal description of what these concepts are to help you understand the math behind them. So what is local truncation error? So it's the error incurred during a single time step. And whereas this error is the accumulation of error across all time steps from 0 up to n. But understanding how much error is committed during one step certainly helps with understanding this error. And how is it measured? What we do is we substitute the exact solution into the numerical method and see what is left over. So look at it this way. The exact solution satisfies the ODE. The numerical solution satisfies the numerical method exactly. So if you plug either solution into the other equation, for example, the exact solution into the numerical method or the numerical solution into the ODE, they're not going to satisfy exactly. There's going to be something left over. Unfortunately, it doesn't really make sense to substitute the numerical solution into the ODE because the ODE, y prime equals f of ty, deals with continuous quantities of functions on defined on a continuum, like an interval in t. But the computed solution is discrete. It's defined only at these equally spaced times, t0, t1, t2, etc. So what we can do, though, is take the exact solution at time, tn or tn plus 1 or whatever, and substitute that into the numerical method and see what is left over. For convenience, what you should do is take the numerical method as it's normally written and divide by h. And also put everything on one side. And the reason for that is so that the numerical method more closely resembles the ODE. So if Euler's method, the way local truncation error is defined, all right, so it's thought of as a function of h, but also varies from one time step to the next. So with Euler's method, I have y at tn plus 1 minus y of tn all over h minus f of tn y of tn. So recall that Euler's method is yn plus 1 equals yn plus hf. So what I've done here is I've moved everything onto one side, set equals 0, and then divided through by h. So if I cancel the h, that's so let me put this up here just so you can see. All right, so Euler's method, which is y n plus 1 equals yn plus hf tn yn. So I substitute the exact solution in for y, move everything onto one side, divide by h, and this is what we get. And thanks, what you can do after that, to get a formula for local truncation error that's more convenient than this, is we could use Taylor expansion. So that would be equal to, so a Taylor expansion of ytn plus 1 around tn, so that's the center, what we would get is, okay, hopefully I can fit it on this line. So I'm going to have h y prime of tn plus the next term, h squared over 2 y double prime. And I'm going to stop a Taylor expansion right here. So I'll have an unknown point, c, and all of this is divided by h. But the thing is, y prime is f of tn y of tn. So here the h's would cancel for this term. So this part, if we break this up into two fractions, will just give me f, which cancels with this f. And then the only thing that's left is we have this h squared over 2y double prime, but that is divided by h. So what we get is h over 2 y double prime at c. And this is how we see that the local truncation error is of order h. So as h goes to 0, the local truncation error also goes to 0 at a rate of h to the first. We saw earlier that this error also goes to 0, order h. So that's actually why we divide by h in dividing. Usually by in a local truncation error, we divide by h so that the order of a local error and the order of this error, which is called the global error, and I'll talk about that more next time when I talk about convergence. The local error and the global error have the same order of magnitude. So this is how we get local truncation error. We substitute the exact solution into the numerical method, divide by h, move everything to one side, and we simplify as much as you can using Taylor expansion to see what is the leading term, in other words, a term with the lowest power of h, because h is going to 0, and that gives us the local truncation error. And it always has this form: some power of h times some constant times some higher order derivative of the solution. Okay, so that's local truncation error, and we'll learn how to obtain local truncation error for other methods as we go. So once you have local truncation error, you have consistency. So a method is consistent if a local truncation error goes to 0 as h goes to 0. Okay. So very simple. And so we see here, if we have any positive power of h in the error, then the method is going to be consistent. And certainly the method needs to be consistent if it's to be useful at all. Then we have a concept of stability. So a method is stable if a change in the initial data, y naught, which could be a vector value quantity, but here I'll just refer to it as a scalar y naught, leads to a comparable change in the solution at any time tn. So that's the informal definition. For the formal definition, come on. Okay. So here we have a change in the initial data. So two different initial data, y naught and tilde y naught. So a change in the solution caused by that change in initial data is bounded in size by some constant k times the change in initial data. And the very important thing here, k has to be independent of h. So I'm going to make a note of that in my informal definition. Okay, so in a way that is independence of h. And this is related to the concept of a well-posed problem. A problem is well-posed if a solution exists, the solution is unique, and the solution depends continuously on the data. So a small change in the problem input does not lead to an unduly large change in the output. So stability is very closely related to that. The idea is that changing the step size h does not lead to a change in how the solution is influenced by error in the initial data. or perturbation of initial data. Okay, so and what we will see is that if a method is shown to be consistent and stable, um, then it is also convergent, and that's something that will be established firmly on Monday. So for today, we're just going to focus on consistency and how we show that. Okay, so I just need to get my notes in order here. Okay. Um, okay. So I'm going to break this down into two parts. How we show consistency for first for one-step methods. Okay. What's bugging me here is yes, these are supposed to be subsections of consistency, and I have it organized that way, but I was hoping to use a smaller font, but it doesn't. So I'm going to label these sections accordingly so you can clearly see these are under consistency. Okay, so the idea is we want to show that first we want to be able to get a hold of a local truncation error for whatever method we have, and then show that as h goes to 0, that this local truncation error goes to 0. That will not only tell us whether a method is consistent, but it would also tell us the order of magnitude of the local truncation error, and also therefore also the global error. Is it low order or high order accuracy? Error order, h squared, h cubed, etc. So, a general one-step method can be written in this form. So yn plus 1 is equal to yn plus h times some function phi that depends on tn, yn, and also yn plus 1. Some books leave this out, but I believe it's necessary to include this yn plus 1 in case the method is implicit. So as an example, for Euler's method, phi of tn, yn plus 1 and h is just equal to f of tn yn. Whereas for another method such as four-folded Runge-Kutta, it'd be a much more elaborate expression that would deal with 4 evaluations of f. That would include t and also h. And I'll show you another example when I go to show local truncation error. So the local truncation error, which I will abbreviate as LTE, is so all we do here is we just rearrange the method and divide by h, and we also substitute the exact solution into the method. So y of t n plus 1 minus y of t n over h minus this phi or phi. Okay, so this is what I'll refer to as tau n of h for the local truncation error. Okay, now we want this to go to 0 as h goes to 0. So let's go ahead and let h go to 0. So this is the derivative at time tn, y prime tn. And what we get over here is Tn, Yn, and then also Yn, because h is going to 0, so Yn plus 1 would converge to Yn, and 0 for h. But y prime at Tn needs to equal f of Tn Yn. So the method is consistent. So once the method is consistent if we have the following, that phi of, substitute Tn, and then substitute y in both places, and substitute h equals 0, that must equal the other side of the ODE, so f of Tn Yn. Okay, oh, actually, I need to fix this because we are substituting the exact solution. Okay, and same thing. Okay, and up here also. Okay. All right. So really, I can be a little more general about this, since y could be anything based on the initial data. So it's to simplify the definition a little bit. If I just substitute in any t and any y, then that'll work. So this is all you have to do to show that the method is consistent. So wherever Yn plus 1 is involved in the method, substitute Yn. Wherever you see h in this part, so not the h out here, but let h go to 0, to substitute h equals 0, and if you substituted Tn and Yn, then it should reduce to f of Tn Yn. So whatever t and y is plugged into phi here, it must reduce to that same t and y being plugged into f. So if it just collapses to f at the appropriate time and y value, then the method is consistent. Now, to show you an example, of a one-step method, but one that's more interesting than Euler's method. The midpoint method is y n plus 1. Okay, I'm going to put this onto a new page. Okay. All right, so the midpoint method is y n plus 1 is equal to yn plus h f. And here we have Tn plus h over 2. And then we have Yn plus, and I have h over 2 f of Tn Yn. Okay, so this is a method I was described earlier. Here we're using the Euler's method approximation of y at time Tn plus h over 2 to fill in for the y value. And then we plug this into f again to get to help us get Yn plus 1. So in this case, our function phi of Tn, Yn plus 1, h equals just the f part here. Okay, so let's copy that down here. Okay, something went wrong. I thought I copied all that, but apparently I did not. Okay. All right. So that's our phi. So we let h equals 0. So what we get is phi of tn, yn, 0 is equal to f. So we set h equals 0, so that term goes away, and that term goes away also. So we're just left with tn, yn. So we get that the method is consistent. I'm going to do another real quick. This one's not featured in the text. The implicit trapezoidal method. That is yn plus 1 is equal to yn plus h over 2. That's f of tn, yn plus f of tn plus h, yn plus 1, because it's an implicit method. Okay. So this is really tn plus 1, but I could also write it as tn plus h, because that's what it is. So this part in the square brackets is our phi. So that equals this part. Okay, and also we have the 1/2. So everything but the h. So what happens as we let h go to 0 is we get f of tn yn plus, here, this term goes away, so it's just ftn. And then yn plus 1, because h is going to 0, that just becomes yn again. So we just get f of tn yn. So again, the method is consistent. Okay. All right. Now, all right. So this is how you show that one-step method is at least consistent. But that doesn't tell us about the order of accuracy. So we use Taylor expansion on the local truncation error. So as an example, okay, so this would be example. I'll show you this. Okay. Okay. All right. So what I'm going to do is I'm going to take you through this. So what we have here, this is the midpoint method. So what we do up here is we do a Taylor expansion of y of tn plus 1 centered at y of tn. So once that happens, and we substitute Taylor expansion in for y of tn plus 1, the first term is y of tn, which cancels with this one. And this is the second term, hy prime, but y prime is equal to f, because it's the exact solution. And then we have this term from second derivative, and then higher order terms that are order h cubed. Okay, which I probably could have stopped the Taylor expansion here in this case, but either way. Then for this part, the f part, we also do Taylor expansion, but this is a multivariable Taylor expansion because we have to as a function of two variables of t and y. So first term, we're expanding around Tn and y of Tn. So that gives me this term, f. And there's a typo here. There should be another closing parenthesis. So I'll have to make a note of that. And then what we have next are first derivative terms. So we have a difference in t values times partial derivative of f with respect to t evaluated at the center. And then we have difference in y values. So that's hf times partial derivative of f with respect to y. And then we have other terms that happen. Then we also have the next terms in the multivariable Taylor expansion will be of order h squared. So I'm not writing those out. Okay, so the next thing is, if I go back to here, I have y double prime. Well, that needs to be expanded. So really what I do is I replace y prime with f. So really I need the derivative of f with respect to t, because y prime is f. So y double prime is a derivative of f with respect to t. But that again is a multivariable Taylor expansion. Sorry, it is not. It is a chain rule exercise that will introduce some expression. So no, sorry, it is not a second Taylor expansion. Sorry about that. So we take f of t and yn, take a derivative of it with respect to t, keeping in mind that y also depends on t. So therefore, we have to need both partial derivatives, and we also need a chain rule. So first, we take a partial derivative of f with respect to t, evaluated at t and yn, and then we have a 1 over 1/2 h squared that's still sitting here, and then I add to that partial derivative of f of ty with respect to y, and then by chain rule, I have to differentiate the y with respect to t. So that gives me y prime, but that is f. So all that goes here. So now what I could do is match this whole fraction against the other part down here. Now keep in mind, all of this up here is divided by h. So I have hf over h, which is just f, cancels with the f down here, which again is missing a closing parenthesis. So this f cancels with this one. Next, I have 1/2 h squared over h, so that's h over 2 df dt, which cancels with the h over 2 df dt down here. So this cancels with this. Here I have h over 2 df dy times f, and here again I have h over 2 df dy times f. So everything, all of this cancels with all of this. And what's left? I have order h cubed over h, so that's order h squared. And I have order h squared down here. So ultimately what we have is order h squared. If we were to write out these terms here, we would find that we would not get any, would not get enough cancellation. We might get some, but there will be something left over. So the not only is the midpoint method consistent as seen earlier, but the local truncation error is order h squared. In other words, midpoint method is second order accurate. Okay. All right. So that's how we show a one-step method is consistent. Okay. All right. So now, what about a multi-step method? So if you look at the general form, all right, so what we have is a sum on the left and sum on the right. So sum for m-step method. Okay, that is equal to h okay. So we do the same thing as before. We substitute the exact, sorry, my apologies, f. It's valuations of f that go on the right side are multiplied by betas. Okay, so the local truncation error for a general multi-step method is tau n of h. So we do the same thing as before with one-step methods. Substitute the exact solution into the numerical method, put everything on one side, set equals 0, divide by h. So now I have 1 over h, m alpha I, y of t, n plus 1 minus I. All right, minus, so we're dividing by h, so that cancels with the h here. And what we have now is beta I f of t, n plus 1 minus I, y of t, n plus 1 minus I. So that's the local truncation error in general. Oh, this can be quite the pain to evaluate. Okay, and actually, you know what? I do need to include something extra here. So, because for most methods, such as Adams methods, they're written in such a way that the sum of the betas is equal to 1. But that actually is not true of all multi-step methods. So I'm actually going to divide not but just by h, but as a normalization constant, I'm going to divide by the sum of the betas, whatever it is. Again, for most methods, the sum of the betas is 1. But to account for those exceptions, I'm going to divide by that. And the reason for that is that way, like this okay, actually, because I divided by h up there, I need to put an h there. So that way, if I broke this up into two fractions, and I let h go to 0, the this part right here over the denominator would converge just to f of tn, y of tn. So therefore, what's over here ought to converge to y prime of tn. So again, this is a normalization convention. Okay, now this can be kind of a pain to do for a general multi-step method, but for Adams methods, we can make things a little simpler. So what we have here is yn plus 1. All right, so all I'm going to do is for Adams methods, they're characterized by alpha 0 is equal to 1, and alpha alpha 1 is equal to minus 1, and all other alphas are equal to 0. Okay. All right. So if I just take it into account here, then what I'll get is y of tn plus 1 minus y of tn. Okay, all over h. And for Adams methods, the sum of betas is equal to 1, so I don't need to include that here. All right, this is tau n of h. Okay. Minus, and for the rest of it, that'll be 1, the h's will cancel, and we'll get a sum of a beta I f of t n plus 1 minus I, y of t n plus 1 minus I. So that's what it reduces to in this case. But what I'm going to do here is keep in mind that the stop it. Okay, I was interrupted by that call. I guess that stops recording. Okay. So in trying to get a handle on the local truncation error for Adams methods, there are two things to keep in mind. That we have y of t n plus 1 minus y of t n can be written as an integral from tn to tn plus 1 of f of s y of s ds, and the f part right here, so sum m of beta I f n plus 1 minus I, that is equal to also an integral of, okay, I should, okay, here I should have h, okay, so this is tn to, also same limits, tn to tn plus 1 of p m for an explicit method. Actually, this is a degree depends on implicit or explicit. I'll just leave it as p of s, where p of t is a polynomial. So that's polynomial. Sorry, that not evaluates. That interpolates f of s y of s at the times tn, tn minus 1, etc., all the way down to tn plus 1 minus m. And tn plus 1 for implicit or Adams-Moulton methods. Okay, so now if I divide both of these by h and have the exact solution substituted in here, really what we have is the local truncation error is equal to the exact integral of f minus the approximate integral of f using this interpolating polynomial, all divided by h. So what we have is 1 over h times the error in the interpolating polynomial, and there is a formula for interpolation error. This is something that's covered last semester, and what we have is, I'll write it out for the explicit case. So mth derivative at some alright, and c is an unknown point, but it does depend on s. M factorial, and what we have is t. Okay, so I have alright, so it'd be t minus t n, t minus t n minus 1, and so on, all the way down to t minus t, sorry, not t, s. I have t in the textbook throughout, so I just want to be consistent. N plus 1 minus. Okay. Oh, looks like I'll have to. Okay, let's see if I can wrap this up before something else goes wrong. So, all right, so I have this. Um, okay. Now I have this integral here is the integral of the polynomial interpolation error. So everything in the integrand here, that is the polynomial interpolation error formula. Um, okay. Um, let me make a note of that. H times the integral of the polynomial interpolation error. This is theorem 741 that was covered last semester. In the implicit case, uh, um, we include, so really we have m changes to m plus 1 in the derivative and in the factorial. And we have include linear factor s minus t n plus 1. This m stays the same, but these m's have to be adjusted. So what will happen is this integral for the explicit case will be of order h to the m plus 1, and then divide by h to get a local truncation error that's of order h to the m. Now, this can actually be simplified a little bit. So weighted mean value theorem for integrals, what we get is, all right. And also making a change of variable. Same change of variable I made last time in multi-step methods, where I map this interval tn to tn plus 1 to the interval 0 to 1. So I have this same derivative expression evaluated at an unknown point. Okay. And I have h to the m minus 1 to the m, and then an integral from 0 to 1. And I'll have s minus u minus 1, u minus 2, all the way down to u minus m du. Now this integral can be worked out. That'll be a constant. Okay, in the explicit case, the implicit case, add a factor of u to the integrand to reflect the that we have s minus t n plus 1. That would become just u minus 0 in here, and we'd have h to the so that constant we worked out, and we'd have h to the n plus 1 um, in that case. So that's how the local truncation error is worked out for in Adams' method. Now, it'd be nice to have something a little more concrete, though. And in fact, we can, not just for Adams' methods, but for all multi-step methods. Because what we can do is, if we go back up here to the general local truncation error, we can perform a Taylor expansion here and here, a multivariable Taylor expansion here, which admittedly is quite the pain. So, um, and if we simplify as much as we can, and I'll show you what happens. It'll take too long to type out, but it's here in the text. Okay, so what happens is, here's the same expression for local truncation error for a general multi-step method, but y of tn plus 1 is replaced, actually, y of tn, not y of tn plus 1, y of tn, and also all the other y values. So all the y values except y of tn plus 1 is replaced by a Taylor expansion. and that's what leads to this. And then over here, we take derivatives of this with respect to t. So unlike before, where we did a multivariable Taylor expansion, it's actually a single variable Taylor expansion in t that leads to this. We're not bothering to expand to partial derivatives of f with respect to t and y. It's not necessary in this case. So, because what we could do is first derivative of y is equal to f. Second derivative of y is equal to derivative of all this with respect to t, and so on. So we can rewrite these as derivatives of y, higher order derivatives. So that opens the door to canceling a bunch of terms, or a group, well, in the case of a consistent method. So if we group terms coming from this summation and this summation, combine them and group by order of derivative of y, and see what is multiplying each derivative of y, then we get these expressions down here, and y of tn plus 1 itself is multiplied by the sum of all of the alphas. Now, this is a local truncation error, so we want as many things to cancel as possible. So for example, if the sum of all the alphas is 0, then this term will go away. If this expression is 0 for selected k, values of k, then these terms of this summation um, will go to 0. So we want as much to go to 0 as possible, and so really it's these constants, C0 and then C1, C2, C3, these are the ones we want to be 0. So this is the final local truncation error for a general multi-step method. And so what we can say is a method is consistent if and only if C0 is 0 and C1 is 0. And the reason for that is, notice we have a power of h denominator out here. So this term is of order h to the minus 1. First term here, k equals 1, is of order h. Divide by h, and it's order 1. So this term and the first term of summation must go away to have consistency at all, to have the error go to 0 as h goes to 0. Now, if additional c's, so C2, C3, etc., if those are also 0, then we get higher order accuracy. So, to get order of accuracy p, we need all the c's up to p to be 0. So whichever one is, the first one that is non-zero, that determines the order of accuracy. So, for example, if C0 up to C5 is 0, C6 is non-zero, then it's fifth order accurate. So then, whichever one of these terms is the first one to not cancel, that gives you the local truncation error. And that formula is here. Although I must point out that there is a small mistake, that this minus h to the p, well, the h to the p part is correct, but I dropped a power of minus 1. So really, it should be h to the p times minus 1 to the p plus 1. So if you negate this, that's the local truncation error. So I'm going to make a note of that here. Okay, so for a general multi-step method by Taylor expansion, n plus 1, it can be seen that the local truncation error is given by the formula, I believe it's 12.29, but let me check. Yeah, 12.29. So the one below that is this formula right here. Except there's a minus sign that needs to be in there. That's something to keep in mind for this problem. which is assigned in the homework. What's the local truncation error of a 4-step Adams-Bashforth method? And that's given in a previous problem. So the idea is you would have to um, work out these constants to see what the order of accuracy is. If then the first one is non-zero, that plugged into here will give you the local truncation error. Now, for a 4-step Adams-Bashforth method, we actually know the order of accuracy. It's order h to the 4th. It's 4th order accurate. Therefore, you can jump, for this problem, you can jump directly to, well, okay, if a problem still requires you to verify these conditions, so you still got to compute them for that reason. So, sorry, you must compute them to confirm. But to get the local truncation error, you know that it comes from C5. So if you compute C5, work out that constant and plug it in here, and don't forget to negate. Well, it was my mistake, so I won't fault you for that if you make it too. But if you get everything else right, so at least the magnitude of a local truncation error to get this problem correct. So it would be multiplied by the 5th derivative of y, and then you have h to the 4th. For a Adams method of any kind, you don't need to include the denominator here because the sum of it's already written so that the sum of betas is equal to 1. Okay, so also this can be written not as just one term, not including this, as long as you evaluate the derivative at an unknown point. Excuse me, instead of just plugging in tn plus 1. Okay, so that's the local truncation error for a general multi-step method and how to confirm the order of accuracy resulting from Taylor expansion. Okay, the last thing I want to point out is predictor-corrector methods. So suppose we use two multi-step methods, both m-step. Now, a predictor-corrector method does not have to use methods of the same number of steps, but just suppose that we do. Here is the predictor, which is explicit as Bashforth method, and then here's a corrector, so a modified Adams-Moulton method, also m steps, with this value from here substituted into f. So this theorem says that if you compute the local truncation error resulting from this method with this accounted for down here, so if you substitute the exact solution here, and also what you do is you take this part, substitute it for yn plus 1 tilde here, and then substitute the exact solution here and in the f evaluations here. So if you work out all of that and use the mean value theorem, then this is what results. This is a total truncation error of the entire predictor-corrector method. So it's equal to the local truncation error of the corrector, is this term, and then times the local truncation error of the predictor times this expression here. Now what's interesting is the whole thing is going to be order h to the m, because the corrector has local truncation error order h to the m plus 1. But the predictor, because it's explicit, will be order h to the m. So this is actually the dominant error term right here. And this gives you a error estimate in terms of the starting values. Remember, a multi-step method needs starting values generated by a one-step method just to be used at all. But at least we have this error estimate in terms of these starting values and the local truncation error of this method. This is similar to the error analysis for Euler's method that was carried out in a previous class. The last comment I'll make is based on a homework problem that I did not assign, that For a predictor-corrector method, you can just predict and then correct one time and then go from there, and that's your final yn plus 1. But what you have the option of doing is, once I get yn plus 1, I can substitute it back into here um, in place of this value and keep iterating until we have convergence. And what happens is, the problem here is to show that the local truncation error is order h to the n plus 1. And the reason why that is if I keep iterating until this converges, then really what I have is I'm just using the corrector. The predictor is now meaningless because yn plus 1 satisfies the original implicit Adams-Moulton method. The benefit of the predictor is that you get a better initial guess than if you just used yn, which you might normally do. So perhaps the iteration would converge in fewer iterations than it would otherwise. So what ends up happening in this case is that this part of the error, the local truncation error for the predictor-corrector method, ends up going to 0, because what ends up happening is what you would get from substituting this in here, that part's going to go to 0 as the iteration converges. Effectively, you're just, like I said, you're just using the corrector. Okay, so this is how we get local truncation error for one step and general multi-step methods, and also for predictor-corrector methods based on multi-step methods. So now that we know how to get the order of accuracy of the method, and also determine whether a method is consistent, so at least the local truncation error is at least order h, if not better, we need to examine stability for both one-step and multi-step methods, and that is what I will do next time.